Hi, I'm Sachin. I'll be explaining problem 1 of the homework 10 of the course EL6303. So the first question says define every process and state these properties and your understanding regarding these properties. So let's go with the first process, the Poisson process. So we define Poisson process x of t as follows. So basically for a Poisson process x of 0 to be equal to 0, and we have x of t1 minus x of t2 to be the number of calls received in t1, t2. So basically for a person to receive a call between the interval t1 and t2, we can relate this to a Poisson process. So in our defining process, we have probability of x of t1 minus x of t2 to be equal to a k. So if I can relate this to a number of calls a person receives in the interval t1 and t2, that's equal to k. So it's given by e to the power minus lambda t1 minus t2 into lambda of t1 minus t2 to the power k by k factorial. Depiction of these entire formula in a graphical representation is a step response basically. So if I can point this as t1 and I point this as t2, so basically this ensemble of the graph depicts as the number of calls that a person receives in t1 and t2. So let's go with the properties of a Poisson process. The mean of a Poisson process is given as lambda into t, and the autocorrelation function r of t1, t2 is given as lambda square of t1, t2 plus lambda minimum of t1, t2. And the expected value of x square of t is given as lambda t the whole square plus lambda t, and the variance is given as sigma square to be equal to lambda t. So let's see how each of these properties hold true. So the mean is given to be lambda into t. It's a linear function of time. It basically signifies that for an event to occur, the more the time we wait, it's always better. So for example, you're there at a metro station. So Poisson process indirectly tells us the more the time you wait. Say at t1, you're right there at a metro station. So t1 plus 10, t1 plus 20, t1 plus 30 increases your chances of getting a metro train. So that indirectly is depicted by the Poisson process. The quantity, the amount of time you got to wait for a particular event to happen over a different interval of time. So between t1 and t2, the mean is defined as lambda into t. So the autocorrelation function r of t1, t2 is defined as lambda square of t1, t2 plus lambda minimum of t1, t2. We know that the autocorrelation function r of t1, t2 is given by expected value of x of t1 into x of t2. So clearly lambda is proportional to time. So as and when the time increases, the lambda increases as well. So we are now calculating the autocorrelation with respect to t1 and t2. So since there are two time intervals, we have lambda square because lambda is associated with one time difference and lambda 2 is associated with the second time interval. So since lambda is constant, we have lambda into t1 into t2. So that becomes lambda square t1 t2. The second part of the autocorrelation function says plus lambda minimum of t1 and t2. So if I can relate back to the example, there are two people standing at a metro station and one of them catches a train at t1 plus 10 seconds and the other one catches at t1 plus 5 seconds. So we're more focused on the t1 plus 5 seconds here because we are more focused on how the event occurs at the first time. So minimum of a difference of time intervals is considered here. So the minimum of t1, t2. Since there's only one time difference that we are considering, it becomes only lambda and not lambda square because lambda is directly proportional to time. So that's relating to the first process. So let's go over to the second process. The second process says Poisson increments. So what exactly is Poisson increments? We've defined what exactly is x of t. X of t is defined as the Poisson process. So we have y of t to be equal to the Poisson increments defined as x of t plus gamma minus x of t by gamma. So what exactly are we doing here? We are defining an event to occur at x of t, and we're taking the difference between t plus n minus the original event divided by the time difference between these two events. So since the name clearly says that they're increments, we denote a small line interval sigma, and then we have x of t plus sigma, a small change in the process. What happens to the entire process when you change the time axis by sigma and you subtract the original process and you divide the entire process by the time difference that you subtracted it? A small change in the time interval sigma is being denoted here. So let's go over the properties of Poisson increments. The first property being probability distribution function. P of y of t is given by n by sigma is equal to probability of sigma into y of t to be equal to n. So basically probability of y of t to be equal to n by sigma is equal to e to the power minus lambda sigma into lambda to sigma to the power n by n factorial. It's basically relates to the Poisson process. Instead of t2 minus t1, we denoted by sigma. We are more interested with the time difference rather than what happens at exactly time interval. So explanation regarding these properties are Poisson process defined by e to the power minus lambda t2 minus t1 into lambda of t2 minus t1 to the power n by n factorial. Like I said, the Poisson increments is basically how the second event occurs when you subtract a particular event, when you shift it with the time axis of say sigma or phi with like phi, n, 10 or anything like that, subtracting from the original process and dividing it by the entire time difference. The second property is mean. So what is the mean of a Poisson increments? It's lambda. We know that for a Poisson process, the mean is lambda into t. So Poisson increments is basically a difference between two events of the same interval divided by the interval itself. So it's basically like lambda into t divided by t. So that gives us lambda itself. The third property being the autocorrelation function. R of t1 comma t2 is given by expected value of y of t1 into y of t2. So the formula is given by 1 by sigma the whole square expected value of x of t1 plus sigma minus x of t into x of t2 plus sigma minus x of t. The standard definition of Poisson increments is being incorporated here. X of y of t1 is defined by x of t1 plus sigma minus x of t by sigma. That goes here. And x of y of t2 is defined as x of t2 plus sigma minus x of t2 by sigma. So 1 by sigma into 1 by sigma becomes 1 by sigma square into the following property. So since t1 and t2 can vary, like for example t1 can be greater than t2 or t2 can be greater than t1, so based on these conditions we have two different formulas. For the modulus of t1 minus t2, the difference of the time intervals is greater than the sigma. Sigma is basically the time difference between these two events occurring. So if t1 minus t2 is greater than sigma, we have the autocorrelation function to be equal to lambda square. If the time difference is less than sigma, we have the autocorrelation function to be equal to lambda square plus lambda by sigma minus lambda into t1 minus t2 mod of it divided by sigma square. So the third process is Poisson impulses. So clearly it's the differentiation of a Poisson process. Poisson process is basically what happens at exactly one time interval, exactly another time interval, say t1, t2. Poisson impulses is the differentiation of the Poisson process, and it's denoted by z of t to be equal to, since it's the differentiation of Poisson process, we can denote it as d by dt of x of t, where x of t is a Poisson process. We can also write this as limit of the time difference tending to 0 into y of t. So this is in relation with the Poisson increments. So since these are Poisson impulses, if I can depict it over the graph, it will just be impulses over different time intervals, say t1, t2, t3. It will just be increments. So the mean, what exactly is the mean of a Poisson impulse? Again, we are just looking into one single time at what happens at exactly one time interval. So at t2 minus t1 or t2 minus t3 or whatever that is. So the mean is again lambda into t divided by t. So that becomes lambda. Autocorrelation function becomes limit sigma tends to 0 r y of t1 comma t2. So that becomes lambda square. t1 t2 gets it goes to 1 because we are considering at that exactly one point of interval. So plus lambda into del of t1 minus t2. Let's go with the next process. The next process is the semi-random telegraph signal. So a semi-random telegraph signal is depicted by a square impulse which is oscillating between -1 and 1. By going by the just raw definition of the term semi-random, so that basically says that x of 0 it's either fixed at 1 and -1. Here we fixed x of 0 to be equal to 1. We call this as a semi-random telegraph signal. A random telegraph signal will be x of 0 oscillating between -1 and 1. So we define the process as x of t to be equal to 1 when k is even in 0 to t and -1 when k is odd in 0 to t. So the mean is given by e to the power -2 lambda t. And the autocorrelation function, again, since here we have two different time notations, t1 and t2, there can be two different cases, t1 greater than t2 or t1 less than t2. So we have the autocorrelation function to be e to the power -2 lambda mod of t1 comma t2, mod of t1 minus t2, sorry. Probability mass function. What is the probability mass function of a semi-random telegraph signal? So probability of x of t to be equal to 1, summation e to the power minus lambda t to the power k by k factorial, e to the power minus lambda t. In the first case, let's consider k to be odd, and the second case, let's consider k to be even. In the first case, considering k to be even function, 1 plus lambda t the whole square by 2 factorial plus lambda power 4 by 4 factorial. Basically, the expansion of cos hyperbolic function of time is given by 1 plus t square by 2 factorial, t power 4 by 4 factorial, t power 6 by 6 factorial, and so on. So this can be rewritten as e to the power minus lambda t cos hyperbolic function of lambda t. Similarly, the sine hyperbolic function of time is defined as 1 plus t1 to the t to the power 1 by 1 factorial plus t cube by 3 factorial, t power 5 by 5 factorial, and so on. So this is a probability mass function. The next process is defined as the random telegraph signal. Here the point of x of 0 can oscillate between 1 and -1. So if x of 0 oscillates between 1 and -1, it takes a random value, so it's called a random telegraph signal. So let's see what is the mean of a random telegraph signal. We defined the random telegraph signal as y of t to be equal to a into x of t. So applying standard definition, like a mean is equal to expected value of the function, so it becomes expected value of a into expected value of x of t. So since x of 0 takes 1 or minus 1. Say, for an example, what is the mean of 1, minus 1, and 0? So clearly, sum of these in numbers divided by the total numbers we are considering. So that becomes 1 plus 0 plus minus 1 divided by 3. So that goes to 0. The same definition is being applied to a random telegraph signal. So that becomes the mean of a random telegraph signal is 0. So what is the autocorrelation function? It follows the Poisson increment and Poisson process definition as well. So the autocorrelation is e to the power minus 2 lambda mod of t1 minus t2. We are more interested in the time difference of these time intervals rather than what happens exactly at t1 and t2. So this goes towards e to the power minus 2 lambda t mod of t1 comma t2. And the next process is random walk. So a random walk is considered to be let's say I relate it to a tossing of a coin. So I toss 5 different coins and I get 2 different heads. I get 2 heads in the first tosses and 3 tails in the next 3 tosses. So if I can depict this over a graph, I have +1 for head. I go up, I go +1 from a graph, and I have -1 when it comes to tail. So I depict the following sequence. So if I can denote this by a formula, x of nt is k into s. Let k denote the number of tails I get in, say I toss 5 coins. The sample space is 5 and the number of tails is 2. So if I get 2 tails, obviously then I get 3 heads in the subsequent tosses. So that becomes ks minus n minus k into s. So if I can substitute these values, it becomes x of n of t to be equal to 2k minus n into s, where k is the number of heads, n minus k is the number of tails, s is the sample space. So the probability mass function is given by nc n of n plus r divided by 2, 1 by 2 to the power n. So how did we get this? We have the Bernoulli trials to be equal to p to the power n q to the power n minus q. So if we toss a fair coin, probability of getting a head is a half. So probability of getting a tail is 1 by 2 as well. So if we do that n number of times, we get 1 by 2 to the power n. And how do we get n plus r by 2? We equate the x of nt, that is 2 into k minus n into s, to be equal to rs, and we get n plus r by 2 if we simplify it. The mean of a random walk, let's define what is the mean of a random walk. So let's define y of yi to be equal to s when sigma is equal to head, and minus s when it's a tail. So basically expected value, that's a mean, is s into p of yi to be equal to s plus minus s into probability of yi to be equal to minus s. So probability of getting a head is 1 by 2 and probability of getting a tail is 1 by 2 as well. So it becomes s into 1 by 2 minus s into 1 by 2. So that becomes s by 2 minus s by 2 to be equal to 0. So the mean of a random walk signal is expected to be 0. So the autocorrelation function is expected value of x of nt into expected value of m of t. That becomes minimum value of m comma n into s square. So the larger the value of variables in either m and n will consequently become independent. Therefore the mean is bound to be 0 in this case. So the last process of this question is what is exactly a Wiener process and the different properties regarding to it. We define Wiener process as w of t. It relates to random walk in the case that it's limiting function of a random walk signal. So w of t is limiting function of s tending to 0, t tending to 0, and n tending to infinity, x of t, where x of t is a random walk signal. The most important property that the Wiener process follows is that the second moment, that's the expected value of w square of t, has a finite non-zero property. So let's go with the different properties. The mean of a Wiener process is expected value of w of t. We know that for a random walk the mean is 0. So basically limit of 0 is again 0. So mean of a Wiener process is 0 as well. Density, what is the probability density function of a Wiener process? Probability distribution function is given by 1 by 2 error function of w divided by square root of alpha t, and probability density function is given by 1 by square root of 2 pi alpha t e to the power minus w square divided by 2 alpha t. What is the autocorrelation function of a Wiener process? We know that the autocorrelation function is of a random walk is minimum of nm and into s square. So applying that to a Wiener process, we just multiply and divide by t. So that becomes limitation of minimum of n into t into mt into s square by t. We know that for a given event, S, the sample space occurring in a given event, is a constant, and the time period that between these event happens is the constant as well. So we denote s square by t as a constant, say alpha. So we have limit of minimum of nt comma mt into s square by t, that's alpha. So we have the autocorrelation function r of t1 comma t2 to be equal to minimum of t1 comma t2 into alpha. Thank you.